This is part 2 of a review of AP Precalculus topics 1.1 through 1.3, which is primarily about rate of change. If you haven't watched part 1 yet, you should definitely do that first. I will try to put a link up here in the upper right hand corner, or you can find the link in the description. This video will make a lot more sense if you watch part 1 first. Number 9. Water is poured into this vase at a constant rate. Which graph most accurately models the function whose output is the height of the water in centimeters and whose input is the number of seconds since pouring began? As the water is poured into the vase, it starts out at the wide part at the bottom. As the water rises, it rises into this narrow part. So as the vase goes from wide to narrow, the rate at which the water is rising is going to go from slower to faster, since the rate that the water rises will be faster in a narrow part of the vase. In other words, the rate of change is increasing for this interval of the function. During the second interval, the vase goes from narrow to wide, so the rate at which the water is rising will go from faster to slower. In other words, for the second interval, the rate of change of the function is decreasing. In the previous video, I strongly encouraged you to memorize this chart to the point where you can quickly write it on a piece of scratch paper before taking your next test or quiz. This information will help you immensely throughout AP Precalculus and next year in AP Calculus. So this chart reminds us that if the rate of change is increasing, then the graph of a function will be concave up. Where the rate of change is decreasing, the graph of the function will be concave down. So in the first interval, where the rate of change is increasing, the graph of the function should be concave up. And in the second interval, where the rate of change is decreasing, the graph of the function should be concave down. So that will help us pick which one of these answers is correct. We just need to look for the one that starts concave up and then switches to concave down. Also, since we are pouring water into this vase at a constant rate, we're not taking any water out. So the water level will be always rising. So any function that will model this should always be increasing. So options C and D we can eliminate immediately because these are saying that the water level drops for a time. Okay, and then looking at this part of graph D, it's saying that the water level drops towards the end. The water level never drops, it's always rising. So it can't be C or D. So looking at option A, we can see that it is concave up at the first interval, and then it switches to concave down for the second interval, just like we wanted. So the answer to number 9 is A. Number 10, the table gives the values of function h for selected values of x. Which of the following conclusions, with reason, is consistent with the data in the table? Two of the options say that the function could be linear, and two of the options say that the function could be quadratic. Let's clear that up first. Here's another chart I asked you to memorize in part 1, the previous video. If a function is linear, then the rate of change will be constant. If a function is quadratic, then the rate of change of the rate of change will be constant. In order to discover what the rate of change is doing, we need to compare the input changes and the output changes. So the first input change from negative 2 to negative 1 is an increase of 1. From negative 1 to 0, that's another increase of 1. From 0 to 1, another increase of 1. We love it when the input changes are all the same, because that allows us to do a sort of shortcut and just look at the output changes And whatever the output changes are doing, that's what the rate of change will be doing. So from 5 to 1, we see a decrease of 4. And then from 1 to -1, that's a decrease of 2. And then from -1 to -1, that is a decrease of 0. So if f of x was linear, the rate of change would be constant. These numbers are not the actual rate of change. Well, actually, I guess they are, since the input values are all 1s. The rate of change is the change in output divided by the change in input. Since these happen to be 1s, -4 divided by 1, -2 divided by 1, 0 divided by 1, that's going to give us -4, -2, and 0. So, special case, these are actually the rate of change. So anyway, we can tell that this is not going to be linear because the rate of change is not a constant. So the answer cannot be A or B. If it's going to be quadratic, then the rate of change of the rate of change should be a constant. In other words, the rate of change should be increasing or decreasing by the same amount for equal intervals. From -4 to -2, we see that the rate of change is increasing by 2. And then from -2 to 0, that's another increase by 2. So yes, we do see that the rate of change is increasing by a constant amount, which does confirm that f could be quadratic. This chart reminds us that if a function is quadratic, then the rate of change is linear. In other words, the rate of change can somehow be modeled by a linear function. In order to choose between C and D, we have to decide if the rates of change can be modeled by the linear function y equals 2x, or if the rate of change can be described by the linear model 2x plus 1. Let's check the first model, y equals 2x. The first x value is -2. Let's see if we plug in -2, will that in fact give us the first rate of change, which is -4? Well, if we plug in -2, 2 times -2 is -4. And that is the first rate of change. So the answer is going to be C. By contrast, if we tried to use the model 2x plus 1, if we plug in the -2, that's -4 plus 1, which would be -3, and that does not match our first rate of change. Just to follow through, let's check the remaining x values and see if we get the next two values for the rate of change. If we plugged in -1 into this model, 2 times -1 is -2. And then, let me switch colors for a quick second. If we plug in the next x value of 0, 2 times 0 is 0, which does match the remaining rate of change. 11. For each scenario below, determine whether the two variables have a positive rate of change or a negative rate of change. Well, two variables will have a positive rate of change when if one increases, the other increases, or if one decreases, the other decreases. In other words, if the two variables both change together in the same way, it's a positive rate of change. When two variables change in opposite directions, increasing one decreases the other, that's when you have a negative rate of change. So let's see, the number of papers you have stapled and the number of staples left in your stapler, well, that's going to be a negative rate of change because every time you staple a paper, you are using up staples. So the more papers you have stapled, the fewer staples in your stapler. They are changing in opposite directions, negative rate of change. Part B, the number of people in front of you in the lunch line and the amount of time until you get your food. As you wait in line, the amount of time until you get your food decreases. But at the same time, the number of people in front of you in line also decreases. Because these variables change in the same way, both decreasing together, this is a positive rate of change. Let n of x equal x squared minus 1. The average rate of change of n of x on the interval from c to 3 is equal to 2, where c is a constant. Find the value of c. So we know that the formula for rate of change, or average rate of change, is going to be n at b minus n at a divided by b minus a. If we are talking about the rate of change on the interval from a to b. This is just the slope formula. This is basically y minus y over x minus x. N of x equals x squared minus 1. We can use this to find an expression for n at 3 and later n at c. We can find an expression for both of these things. So n at 3, that's going to be 3 squared minus 1. That's 9 minus 1, which is 8. And then n at c, well, that just means plugging in c for x. So that would be c squared minus 1. So let's substitute both of these into this expression. So for n of 3 is 8, so that's going to be 8 minus. Be careful to use parentheses right here. When you have a binomial with a negative in front, that's going to eventually have to be distributed. So we need the parentheses to make that happen. So we have the c squared minus 1 and put in for n at c. And this is over 3 minus c, which equals 2. So our goal is to solve this for c. If we do the distributive property, as I mentioned, then we're going to have 8 minus c squared plus 1 over 3 minus c is equal to 2. I think I'm going to do two things at once now. I'm going to multiply both sides of this equation by the denominator. So this 3 minus c is going to wind up over there. Also, let's go ahead and do the 8 plus 1, and we're going to get 9. So on the left side, we're going to have 9 minus c squared is equal to 2 times 3 minus c. So distributing the 2 gives us 9 minus c squared is equal to 6 minus 2c. Okay, I think I'm going to pick up right here. So I'm going to get everything on one side of the equation. I really want the c squared to be positive. So I am going to move this over there. So I'm going to add c squared to both sides. Maybe I'll show this in another color. So I'm going to add my c squared on both sides. And to move the 9 as well, I am going to subtract 9 from both sides. So that's going to give me 0 equals some stuff. So I added the c squared, so I'm going to go ahead and put that in the front. So I have c squared right there. The minus 2c, there's no like term for that, so I'm just going to go ahead and put the minus 2c next, unchanged. And then we have the 6 minus 9, which is negative 3. This is going to be factorable. So let's go ahead and factor this. And while I'm at it, I would prefer to have the 0 on the right-hand side for aesthetic reasons, so I'm going to put it over there. When we factor this, c squared can only factor as c times c. 3 can only factor as 3 times 1. Inner plus outer must equal middle. So I'm saying inner, I'm talking about these two. That's 3c. And outer, I'm talking about this times this. So that's 1c. Inner plus outer must equal the middle, which is negative 2c. We control the signs here. So to get a negative 2c, I would want a negative 3c and a positive 1c. So here's my negative 3c, and a positive 1 here gives me the positive 1c. So we factored it. We can finish solving using the zero product property. In other words, set each one of these factors equal to 0. So setting c minus 3 equal to 0 and solving gives us c equals 3. Setting c plus 1 equal to 0 and solving gives us c equals negative 1. However, one of these values is obviously extraneous. C cannot equal 3. You can see that right here. If we put 3 for c in the denominator, that's 3 minus 3 is 0. You cannot divide by 0. Also, that would make the interval be the interval from 3 to 3. Well, that's no interval at all. There's no space there, so you could not have a rate of change. So either way you want to think about it, the 3 doesn't make sense. So C is simply negative 1. Number 13, find the average rate of change of k of x on the interval from negative 5 to 3. So as you saw before, the formula goes like this. It's going to be k at b minus k at a. So k at 3 minus k at negative 5. All right, that's y minus y of our slope formula, divided by x minus x. So 3 minus negative 5. K at 3. So here's 3. Here is k at 3. That is negative 1. So we have negative 1 minus k at negative 5. Here's negative 5. Here's k at negative 5. That is 4. So negative 1 minus 4 over 3 minus negative 5 is the same as 3 plus 5. So that's going to be negative 5 over 8. So that's the answer to number 13. 14, find the average rate of change of p of x equals 3 minus x squared on the interval from negative 1 to 3. Show your setup. So again, we're going to do p at b minus p at a. So p at 3 minus p at negative 1. That's our y minus y of the slope formula divided by x minus x. 3 minus negative 1. Off to the side, we can find the value of p at 3 and p at negative 1. In fact, I'll just do it right here. So p at 3 is going to be 3 minus 3 squared. So that's 3 minus 9. Now, maybe I'll just show a little bit of work here. So that's 3 minus 9, which is negative 6. And then p at negative 1, that's going to be 3 minus negative 1 squared. Negative 1 squared is positive 1, and 3 minus 1 is 2. So let's substitute these values in to the numerator. So that's going to be negative 6 minus 2 divided by, and 3 minus negative 1 is the same as 3 plus 1. So that's going to be negative 8 divided by 4. In other words, the answer is negative 2. Number 15, find the average rate of change of j of x, which equals this, on the interval from negative 1 to 3. So let's do the same thing again. In fact, this time I'm thinking a little bit ahead. We know that ultimately we are going to need j at 3 and j at negative 1. So it might be cleaner to calculate those first. So j at 3. Plugging in a 3 right here, that's 4 times 3, that's 12. Maybe I'll show a tiny bit of work. So that's going to be 12 plus 2 over 3 minus 1. That's 14 divided by 2, which is 7. So that's j at 3. How about j at negative 1? Well, if I plug in negative 1 right there, that's going to be negative 4 plus 2. And then I'd have negative 1 minus 1. So that is going to be negative 2 divided by negative 2, which is positive 1. So let's go ahead and set up the expression for rate of change, which is going to be j at 3 minus j at negative 1 over 3 minus negative 1. We just found j at 3 and j at negative 1, so we can go ahead and substitute those values in. So that's going to be 7 minus 1. 3 minus negative 1 is the same as 3 plus 1. So that is going to be 6 over 4. So the average rate of change is 3 over 2. Number 16. The table describes rates of change of a function f for selected intervals of x. Part A. On what intervals is f concave down? Here's the chart that we have memorized. We know that f will be concave down when the rate of change is decreasing. The only interval that we know that the rate of change is decreasing is this interval from 6 to 8. Let's see, part B. On what intervals is f increasing? According to our little chart, f will be increasing when the rate of change is positive. We only know that the rate of change is positive on the interval from 4 to 6. So that's the answer to B. Number 17. Sketch a function on the axes provided with the following properties. G of x is increasing on the intervals from negative infinity to negative 2. Okay, so negative 2 is right here. I think I'm going to go through and take note of all the x values that they mentioned. So I see a negative 2. I see a positive 2. So that's here. And I see that 0 is also being mentioned. Okay, so these are all the intervals involved. Now let's go back. G of x is increasing from negative infinity to negative 2. So it's going to be increasing over here. And from 2 to infinity. So it's going to also be increasing over here. G of x is going to be decreasing between negative 2 and positive 2. So I don't feel like I have enough space. Can I squeeze in decreasing? Okay, fine. Decreasing in both of these intervals. Decreasing, decreasing. Now we're going to switch and talk about concavity. So I think I'm going to switch colors a little bit. G of x is concave down on the interval from negative infinity to 0. Okay. So that means it's going to be concave down in this interval and this interval. And then concave up from 0 to infinity. So it's going to be concave up on this interval and this interval. Okay, this is enough information for me to begin sketching the graph. However, it also helps me to pay attention for wherever the graph changes from increasing to decreasing or vice versa, because that's going to be a horizontal tangent line. If I go from increasing to decreasing on a smooth graph, that's a horizontal tangent line. If I go from decreasing to increasing, horizontal tangent line. So, I see that we changed from increasing to decreasing right here at -2. I'm going to put a little dash here to remind myself to make a horizontal tangent line. Same thing happens at 2 as we change from decreasing to increasing, horizontal tangent line. Now I'm ready to go. So, as I draw my first interval from -infinity to -2, I need to draw the graph so that it is increasing and concave down. It doesn't matter where you kind of start drawing from. So your graph could be a little bit higher or lower than mine. Just make sure that it is increasing and concave down in this first interval. So here I go. All right, so increasing and concave down, and I'm making sure to end up at a horizontal tangent line. So something like that. In this next narrow interval from -2 to 0, I need to draw the graph so that it is decreasing and concave down. So I'm just going to continue this pattern, decreasing and concave down. In the next interval, I need to switch to concave up and decreasing. And I should end at a horizontal tangent line. So I'm switching my brain to concave up mode, okay, and ending at a horizontal tangent line. In the last interval, it should be concave up and increasing. So as I finish the graph, I'm going to draw it in such a way that it is concave up and increasing. So your graph should look something like this shape, but again, you could have drawn it higher or lower and it would still be correct. 18. On what intervals is f of x both decreasing and concave down? F of x is decreasing, meaning it's falling from left to right, from -infinity to -2. And then it's increasing for the middle interval, and then decreasing again from 4 to infinity. So that's decreasing. What about concave down? Concave down is like this, you know, like an upside down bowl shape, like an umbrella. So I can tell that the function is concave down in this interval. So we're looking for the interval that is both of those at the same time. So that is going to be this part of the graph right here from 4 to infinity. Or from 4 to 6 if we assume that the graph sort of stops right here. Okay, how about the intervals where f of x is both increasing and concave up? Well, the curve is increasing on this middle interval right here. So the question is, what part of this is concave up? So it will be concave up for the part of the graph that is doing this sort of a bowl shape. So it switches right about here. So the part I just highlighted in blue is concave up. So what interval is both? Well, that's going to be the interval from here to here. That's -2 to 1. Number 19. The table gives values of the function f for selected values of x. If the function f is linear, what is the value of f at 11? The significance of this part, the function is linear, is that the rate of change will then be constant. So the rate of change is going to be constant. So let's use the table of values to figure out what the rate of change actually is. Let's start with the changes in input values. From -15 to -10, that's an increase of 5. And from -10 to +5, that's an increase of 15. So we have to be very careful. Since the input changes are different, we cannot just answer questions based on the output changes. We have to actually calculate the rate of change. let's start with the output changes. From -2 to 1, that is an increase of 3. And then from 1 to 10, that is an increase of 9. Okay, so the first rate of change is 3/5. Okay, rate of change is 3/5. According to our prediction, the rate of change should be constant when the function is linear. So it will not surprise us that if we were to look at the second pair, it would be 9/15. Well, that just reduces down to 3/5. Here is the rate of change formula with which we are familiar. It's basically y minus y over x minus x. We can begin to set up the rate of change formula starting with this value that we're looking for. So instead of f at b, I'm going to put f at 11. Okay, so this is y minus y. F at 11 is basically a y value that we are looking for. So we need to do y minus y. So we need to do f at 11 minus another y value. Let's just pick 10. So our y minus y will be f at 11 minus 10. Now we need to divide by the corresponding change in x. We need x minus x. So f at 11 is the y value. 11 itself is the x value. The x value that goes with 10 is 5. So my x minus x will be 11 minus 5. So this will give us the rate of change on for this function. But we know that the rate of change is 3/5. We just found it. So we can go ahead and put the rate of change right here. So this fraction should give us 3/5. The only unknown in this whole expression is f at 11. So we're simply going to do some arithmetic and basic algebra to isolate the f at 11. So I'm going to have f at 11 minus 10. And let's just go ahead and do 11 minus 5, which is 6. And that is equal to 3/5. If we multiply both sides of the equation by 6, multiplying by 6 on this side is going to be like multiplying by 6 over 1. That's going to wind up as 6 times 3, which is 18. So multiplying both sides by 6 cancels out this 6 in the denominator and gives us f at 11 minus 10 equals 18 over 5. Our last step is to add 10 to both sides. So that's going to give us f at 11 is equal to 18 over 5 plus 10. To actually add, we need like denominators. So this is going to be f at 11 is equal to 18 over 5. 10 is the same thing as 50. That's not a good 50. 50 over 5. That's the same thing as 10. Now I have like denominators. So adding these together, this is going to be 68 over 5. So that's why the answer is A.